Central College, and we are Treaty Department of Physics and Astronomy at Ohio Wesleyan, and Zijie Poe is going to present.
Hi, I'm Zijie, and the research I'm working on is synchronization of coupled Josephson junctions. So what is a Josephson junction? A Josephson junction is made up by two superconductors, as shown in gray. And this is the wave function of a superconductor. And the two superconductors is separated by a non-superconducting barrier. And this system is, as a whole is called Josephson junctions. And when a Josephson junction is biased by a current, which we label as IB, there's a supercurrent that tunnels through the junctions. So the whole system will act as a superconductor as a whole. So, so a Josephson junction has a critical current like a superconductor too. And this is the schematic of a Josephson junctions. And when the bias current is smaller than the critical current, the current through the junction obeys this equation. And the theta 1 and theta 2 is the phase of the superconductor. And phi is what we call the Josephson phase. And in this case, there is no voltage drop. However, when the bias current is greater than the critical current, the voltage drop across the junction obeys this equation. And h bar is Planck constant, E is the charge of electron. And d phi dt, we label that as phi dot. And so to study the synchronization, we need a model. And the model that we use is called RSJ model, resistively shunted junction model. In this model, the current through the junction are separated into two different channels. The first channel is supercurrent channel, and the second channel is resistive current channel. And so the total current through the junction is the sum of the current through the two channels. And this is the equation that we get, and this is the main equation that we will use for our research. And since the voltage drop across the junctions obey this equation and is a function of time, the voltage across the junction oscillates in terahertz region. We can calculate that rather easily, but we don't have time to do that now. So because it oscillates at terahertz, it emits terahertz radiation. But the power that it emits for one junction is in the picowatt range, which is very small and not useful. So we can think of having more than one junctions, but the terahertz radiation might not be in phase with each other. So we might not have maximum power output. But experimentally shown that if we have more than one junctions coupled geometrically, we can increase the power output to milliwatt, which is 1 billion times stronger. So that is really helpful. So a way for us to think about a junction is a dots moving around a circle. So like here we have 4 dots. So it's like having 4 junctions. And when the 4 dots are not synchronized at all, they move at different frequency and different phases. However, when they are phase synchronizing, they might start out with different frequency and different phase, but they will eventually end up with having the same phase and same frequency as shown here. So to quantify the synchronization, we introduce a parameter called phase order parameter. And in this parameter, when there are full synchronization, this parameter will give us a value of 1. And when the phases are just moving randomly, it will give us phases of 1 over square root of n. So to geometrically couple the junctions, we arrange our junctions in this array. And this is what we call a bracket. We have 4 junctions here. The 2 horizontal junctions are the main junctions that will emit the terahertz radiation. And these 2 junctions are just the coupling mechanism. And because we are theorists, we want to work with dimensionless quantity. So we divide all the currents. So we divide all the currents by the average currents of the 2 horizontal junctions. And we denote the dimensionless quantity as small letters. However, for this one, instead of I, C naught, we write it as alpha. And alpha is our coupling mechanism. And we do the similar thing to time. So our time is also dimensionless time. And then we applied RSJ model and conservation of charge at each node. So we'll get 4 equations, 4 nonlinear coupled differential equations, one for each junction. And then we calculate, and then we numerically calculate the phase order parameter. And we plot the phase order parameter. We have a IB for the y-axis and an alpha for the x-axis. Alpha is coupling strength. And the whiter regions means that the R value is higher. So this region, so we can separate this plot into 2 regions. So this region is the synchronized region, which we label as S. And this is the unsynchronized region, which we label as U. So in the U region, the 2 junctions that are shown in blue here, they are not synchronized, but in the S region, these 2 junctions are synchronized. So because we want to have as many junctions as possible, we can attach another plaquettes to what we have, and we get 2 plaquettes as shown here. And then we also shunted the 2 plaquettes by a junction which has a critical current of ICS. The reason that we want to have this junction is because without this junction, we will never get the S region. So let's compare the 2 plots that we have. Okay, for the first thing to take note is that the x-axis is different. One is from 0 to 0.2, and the other is from 0 to 1. And we see that we still have the U region at the same area, and the S region is much smaller, and now we have another new region, which we label as S sub LR. So in that region, we say the arrays are partially synchronized. Because the 2 junctions that are colored in blue are synchronized, and the 2 that are in brown are synchronized, but the blue and the brown colored junctions are not synchronized. So as a theorist, we want to find an equation for the boundary here. The reason that we want to find the boundary is because if we know the boundary, then experimentalists will be able to fabricate the junctions with the parameters so that it will always synchronize. And so to find the boundary, we did some analytical work. So the first thing to take note about is what we call multiple timescale analysis. So let's look at the phase synchronization again. We see that there are 2 timescales. The fast timescale is the time for it to oscillate around a circle once. And the slow timescale is the time for all the oscillators to synchronize to phase. And we denote the fast timescale as T0 and the slow timescale as T1. Okay, so this is the equation that we get when we did the conservation of charge at each node. And this is just one of the equations. We have 4 of those similar equations. And the A, B, C, D, E are just constants. And for perturbation theory, we'll always need a small quantity. And so we define the small quantity as epsilon, and we define that as 1 over IB. So we assume that IB is large. And then we multiply the order of the 4 equations by epsilons. And then we introduce multiple timescale to our analysis. So, so for the time derivative of phi, we separate that into a fast timescale and a slow timescale derivatives. And when we rewrite the equations, this is what we get. The script D0 is just the partial derivatives, it's just this term. And then we apply perturbation on our phase. So our phase is divided into a 0th order phase and a 1st order phase. And we separate our equations into the 0th order equations and the 1st order equations. And the main idea of perturbation theory is that we will always need to solve the 0th order equations. And then we get the solution of the 0th order equations and substitute them in the 1st order equations, and then solve the 1st order equations. So we did that, and this is the result that we get. So these 2 equations are the RSJ equations that for these 2 junctions. And these 2 are the equations that we get from our analysis for the same junction. And we see that all the phases are only dependent on T1 timescale. T1 timescale is the slow timescale, which captures the synchronizing behavior. So that's what we want. And so to find the parameter for full phase synchronization, so we think of like when they are in phase synchronization, the dots are overlapping each other. So the difference between their phases is 0. So the time derivative of that is 0. So we set that to be 0. And when the 2 are synchronized, the coupling mechanism doesn't do any work because they are already synchronized. So we can let the time derivative of that to be 0 too. And then we solve for sine of psi1 and sine of psi2. And this is what we get. And because sine is always smaller or equals to the absolute value of 1, so we set it to be 1 and then solve for IB as a function of alpha. And we plot out the equation that we get. And this is the line, the pink line is the equation that we get for these 2. And we see that they are in pretty good agreement with our numerical work. However, the issue is that we don't get a line for this boundary. So we think that we don't get the equation for that boundary is because this boundary is mainly in the small IB regions. Like most of the time is in a small IB regions. And we assume that IB is large. So that might be the cause. And then so now what we are working on is instead of using IB, 1 over IB as a small quantity, we'll use ICS, which we set as 0.1. So that will be a small parameter that we'll use. And so I would like to thank my collaborators for this summer, past summer, and my advisor, Dr. Trees, and OSSRP and SFRU. Thank you.